Hey, this is Joseph Ryan Bernicki with Dr. Osbay's Aerospace Design of Aerospace Experiments class. And today we're going to be taking our wind tunnel that we designed in Project 1, and we're going to be taking the 50 hertz condition of that wind tunnel, which is about a test section velocity of about 12.7 meters per second. We're going to take the profile of a NACA 2412 airfoil. We're going to import it into the geometry, and then we're going to go ahead and simulate it and take some readings such as we're going to produce some contours such as our static pressure contour. We're going to do our velocity contour, and we're going to find out some stuff like coefficient of drag and what else? Oh, we're going to do some streamline. We're going to show a streamline simulation as well. So we're going to go ahead and get into that. So this geometry of the NACA 2412 airfoil, we took the coordinate system off of a website on the internet. We took it, put it into an Excel file. I took that Excel file and turned it into a notepad that SolidWorks could read. So this is the coordinate X, Y, and Z coordinate system. I went ahead, I took that, I imported it in using the curve through XYZ points. So that is what we resulted at. I made the wind tunnel so that the origin was right at the center of the test section. So the geometry that was imported was put right at the origin, right where I wanted it to be for analysis. So after creating the geometry in SolidWorks, we're going to go ahead and save it as an IGS file. Now you can save it as a variety of different files, and Ansys accepts a variety of different files. I just chose an IGS file because that's what I'm used to, and it always seems to work out for me pretty well. So we're going to exit that because we don't need it anymore. We're going to go ahead and open up Fluid Flow Fluent. We're going to open up a new one of those. Oh, what did I do? Is that a new one? Yeah, here it is. So we're going to take this one right here, and we're going to go into properties on the geometry, and we're going to select a 2D analysis because that's how we want everything to be going through. We're not doing 3D yet. I don't think we're going to end up doing 3D in this class. I might do it for fun, but we'll see. NACA windtunnel.igs. That's the file that we want to import. We're going to go ahead and import it. Ansys took it beautifully. And there we go. So now we're going to go ahead and hop into the mesh. All of those previous projects are going. Those are from other situations I had to test with this wind tunnel using a flat plane, using a hemisphere, I guess in the 2D representation it's a half circle, but either way. So we're going to go into the mesh here. We want the element size to change. I don't want it well, first of all, let's go ahead and actually update the method because I don't want to use that method. So we're going to select this geometry right here. We're going to use the triangle method, which is perfect. And then we're going to go ahead and generate that. Boom. So now that is like that, we want this mesh to be finer. This isn't exactly how we want it. 5 times 10 to the negative 3 is what we've been using in the past, so that's what we're going to continue to use. So 5 e to the negative 3, hit enter, and now we're going to go ahead and generate that mesh. So now that's generating. It's going to take some time to generate because it's a pretty fine mesh, but we want it to be fine. We want I personally have the computer to handle that kind of simulation, and it'll be just fine. So, but the thing is, this mesh is fine all throughout the wind tunnel, but that's not our area of interest. Our area of interest is going to be the NACA airfoil. So the mesh is fine on the settling chamber, contraction chamber, and even on the outside of the test section. This is all okay. But when I'm looking at the airfoil, I want the mesh to be very fine because I want as much information around this airfoil as I can gather. So we need to make this mesh finer. So what we're going to do is we're going to go into this mesh here. We're going to do sizing. That's going to add this for us. Now the geometry that I want to apply is not the geometry of the surface like we did previously. We're going to select the edge. We're going to control click, every single little surface around this NACA airfoil. And there's a lot of little surfaces, so make sure you're careful and click every single one. And we just want to bring this green line all the way across. There might be a more efficient way of going about this, highlighting every single edge. Alas, I'm not familiar with that method, so this is what we're going to do. So we just applied that 39 edges. Element size, I want to be finer, so I'm going to do number of divisions just because that's a little easier for me, and we're going to do 40 number of divisions along each one of those elements that we just clicked. So 40 times 39, that's how many separations we got. That's how many points of information we're going to be grabbing along the surface, which is important. The surface contains a lot of important information that we want to know. Information about the boundary layer. The no slip condition is applied to these walls as well, so we should see zero velocity right along the right along the edge of that surface, ideally. So and we do have the non-slip condition, or we will. I'm not sure if it's applied yet. I can't remember, but I believe that's something we're going to apply in the next segment, the simulation segment. So I don't want to get too far ahead of myself. So the mesh here, we're going to go ahead and just regenerate that, because you're going to see this area is going to become much more fine. So again, that might take some time, but we'll see. Sweet. So yeah, as you can see, the mesh is way finer. We're going to get a lot more data around this airfoil, which is what we want. More the merrier. We have computers, so we don't have to sit there and crank out numbers by hand. So Excel is a beautiful thing. So cool. So now that this is the way it is, we need to make sure that we are naming the areas that we want. So geometry right here. We're going to want to insert named sections. Insert name selection. That's what we want to do. Perfect. All right. So the geometry that we're going to want to select, we're going to want to select this edge, and we're going to select this one right here. Apply that. We're going to rename this velocity inlet. And now we're going to go through and do the rest of that. We're going to continue to do that. So we're just going to insert name selection. We're going to do it a couple times. So let's go ahead and double click on this one, the geometry. We're going to want this to be the wind tunnel walls. So let's go ahead and select the walls of our wind tunnel. Perfect. And now also we can select this as walls of the wind tunnel as well. And again, it's a lot of clicking. Make sure you're holding control all the way throughout. Perfect. We will apply that, all 55 edges, because it should be, what was our last number? 30 something plus 8, because I think we got 8 on the, if I remember right. But either way, so that's named. We're going to go ahead and rename this wind tunnel walls. Selection 2. We're going to choose this to be right here. Edge select. Apply that. And then we're going to rename this. Rename as our pressure outlet. And then selection 3, we're going to go ahead and select our face, and then this face is going to be our wind tunnel interior. So rename wind tunnel interior. Perfect. So now we have all these selections labeled out. This is what we're going to use to actually set up the conditions of our simulation. So we're going to go ahead and just save that, make sure everything's nice and tidy, and we're going to exit out of it. Cool. So now we also want to make sure that our mesh is updated. And again, this can take a second, but just got to be patient with Ansys. Cool. Mesh is updated. Awesome. So now we're going to go ahead and edit our setup. We're going to do double precision. Crank it up to 4 solvers processes, because that has to do with the number of cores you have. I'm on an 8-core processor, so 4 is just fine. 2 would be fine too. You can run it with less or more. Don't worry about that too much. If you don't know, then just run 2. It'll be okay. Okay, models. Energy. So we want energy to be on. Energy equation. On. Our viscous model. Let's go ahead and verify that we're at the right one. We're not. We want to do K epsilon. We're going to do K epsilon. We're going to do it with enhanced wall treatment. Pressure gradient effects and thermal effects are going to be in this simulation. So that is good. And now we can go ahead and minimize this for the moment. Let's go to materials. Let's make sure our fluid, air, and all of those look right. So that's all good. Solid doesn't matter. Fluid, here we go. Wind tunnel interior fluid. That's exactly what we want. So that is good. Other boundary conditions, we have our inlet, velocity inlet. We want this velocity inlet to, the speed of it is going to determine what our speed of the test section is. So we need our speed at the velocity inlet to be about 1.84 to get a speed of 12.7 in the simulation, roughly. So we're going to go ahead and apply that. And then we're going to exit. So let's make sure that our interior it went to our name section that we had before automatically. We have our outlet, went to the pressure outlet automatically. So we're going to exit that. And then our wall, we got the wind tunnel walls, and that includes our airfoil that we have in there for analysis. So let's double click that. Interior, perfect. Pressure outlet, perfect. Velocity inlet, wind tunnel walls. So everything is looking the way it is, or the way it's supposed to be. The way it is. Everything's looking the way it is, yeah. Okay, so now we're going to go into report definitions, new, force report, drag, because some of the information we want is going to be drag coefficient and the drag force as well we can get. So let's go ahead and let's do drag coefficient first. Drag coefficient NACA 2412. All right, wind tunnel walls. Ooh, drag coefficient. I don't want the drag coefficient of the wind tunnel walls. So this is what we're going to do. This is an easy mistake that we can fix. So we're going to go back. We can just exit out of this. It should all save. We're going to go back and actually edit our mesh because we don't want to incorporate the NACA airfoil into the wind tunnel walls because I don't want the wind tunnel walls affecting my coefficient of drag and force of drag, because if I have them under the same name selection, it's going to calculate it with the surface area of the interior of the wind tunnel, which is not accurate. So we're going to actually create another name selection, and then this name selection is just going to be our NACA airfoil itself. So the geometry, we're going to go ahead and zoom in on the NACA airfoil. We're going to control click every single one of these edges again. I really need to look up if there's an easier way to go about selecting everything. Okay, so perfect. Now it looks like every single line is selected. Apply that selection, rename NACA 2412. Now for the wind tunnel interior, or the wind tunnel walls, we actually need to go back and adjust this to none of that. So we want to select this, this, this. Separating it out a little more than before. Perfect. So that should be that. So apply that 16 edges. $55. Perfect. So that adds up. So we now have the NACA airfoil, which is right there, and the wind tunnel walls. So those are going to be separate. So that's perfect. So now we can save this, and then we can exit this, and we can go back to our simulation. So again, we have to go through and we have to update this to make sure that it takes note of the changes we made, so that we can go back into our setup and fix everything. Which again, it's not that much fixing, it's just it's something that needs to be done, or else we're going to be getting inconsistent results. The simulation only puts out numbers that are as good as the numbers you put in. So perfect. So now we're going to go back into the setup. The upstream mesh is changed. That's because of our new naming selection, and we want that to reflect in our setup. We're still going to do double precision, still have 4 solid processes. And now we're going to reboot this. Okay, now like I was saying, most of the stuff should have saved that we already did before. So let it load, let it think. Don't show this message. I know I've clicked don't show this message 4 times. Found new zones with incoming mesh. Good, that means that's registering the change we just made. So models, our energy is still on. We're still doing the standard K epsilon with the enhanced wall treatment. Standard, enhanced wall treatment, pressure, okay, that's all good. Just going through and double checking everything, making sure that nothing changed. Materials, fluid, air, that's all good. Solid boundaries, fluid, wind tunnel interior, that's the same. Boundary conditions, inlet, velocity, inlet. Let's double check to make sure that our inlet velocity didn't go back to the default, which it didn't. We're still at 3.184 meters per second, which should result in the 12 plus meter per second of the test section. Outlet, pressure outlet is still labeled, wall is still labeled, and now look, it automatically went through and gave us 2 walls. We have the wall of the NACA 2412 and we have the wall of the wind tunnel walls, and that's going to come into play when we do our drag coefficient and drag force calculations. We would have been including all of the drag from the wind tunnel walls, which would have thrown our numbers off a lot. So let's go ahead and go back to what we were doing before, and that was in the report definitions. So yeah, we're going to edit, we're going to go new, we're going to do force report, drag. we're going to name this drag coefficient NACA 2412. Drag coefficient selected. Now we're going to go ahead and select NACA 2412 for this. Print to console. NACA 2412. Okay. Sweet. So now that we have that, we're going to go ahead and create a new one, a new force report. We're going to do drag again. We're going to do drag force NACA 2412. Drag force NACA 2412. Print to console. Okay. Boom. So now we have the drag coefficient, drag force, which we're going to be taking the drag force and we're going to go ahead and calculate the drag coefficient from it, and we're going to plot all the drag coefficients as well. I'm just doing this to get another graph up on so that we can look at it. So we're going to go ahead and close. Now that we have our report definitions on there, we have our boundary conditions set, materials are set, our models are set. Let's go ahead and initialize it. Graphics. Let's go ahead and put up a couple graphics real quick. Or, well, we can do that after. We can do that after our calculations. Let's go ahead and initialize. 60 iterations on the initialization just to make sure that it goes through initialize. And again, this takes a while. It's going to count all the way to 60, do every single step it needs to make. All right. And now, cool. So now that we're done with that, we're going to go into our calculation, run calculation, number of iterations. Right now we're at 0. We're going to do 800. 800 is a lot for this. You're going to see as it goes through and calculates the drag force on the airfoil, it's going to solve it and come to a pretty consistent answer after like 100. But I've been running 800 throughout for all of my other ones. I'm going to keep it consistent. It doesn't take that long. So we're going to go ahead and calculate it and let the computer think. But you'll see as we're going through the iterations, it goes through and converges on a certain value. Perfect. Alrighty, so now that our calculation's all done, we can go ahead into the graphics here and we can make some new contours. Contour 1, we're going to want to do the pressure, we're going to want to do the static pressure, smooth, we're going to want to do it of the wind tunnel interior, and let's go ahead and save and display. Cool, so static pressure is going to decrease as the velocity increases because dynamic pressure is taking more of that, which is perfect. Static pressure, high increase towards a stagnation point. That is exactly what we wanted to see. And perfect. So it looks like we have lower pressure on top, higher pressure on the bottom. Awesome. Lower pressure, also lower static pressure on top because the velocity of the flow on the top of the airfoil is faster than on the bottom. So that's exactly what we would want to see. This looks like a realistic depiction of this. So now let's go ahead and let's do the velocity. So let's go into contours again. Let's create a new one. Let's do a contour of the velocity magnitude. We don't want to name contour 2. Velocity contour NACA 2412. Save and display. All right. So are we getting what we're supposed to? Basically around 12.7 roughly. Again, we can't tell exactly off of this scale, but 12 point something meters per second flow of velocity inside of this. And wow, look at that. And the boundary layer, the non-slip condition is taking hold in this because we have 0 velocity right on the edges of the airfoil, which is awesome. Wow. Perfect. So now we have the velocity contour. We have the information that we need for the drag force, which I'll go ahead and we can actually take report definitions or I can take the drag force here and just compute it. And then so our drag force is coming up as 0.22 newtons. Our drag coefficient, compute it, 0.3731. So again, I'm gonna take the drag force and actually do calculations to check on this number right here, but that's what it converged upon. So these are the values we're going to be using. Now we have the velocity contour, we have the pressure contour, static pressure contour, we have the drag force, we have the drag coefficient in theory, and we are going to go ahead and do a streamline model of this. So let's go ahead. Now I have successfully done it actually in this simulation using the results tab over here to do path lines. I've done it successfully once. I haven't been able to do it successfully again. So I'm going to do it the way that I know I can do it right. So I'm going to go ahead and exit out of this application. We're done with it for the time. Yeah, sure, save settings. Now we're going to let that close. Cool. Solution. We're going to go ahead and update that. We should have gotten a solution. That took an incredible amount of time to actually come and generate a solution. So I'm sure I'm going to edit out that whole waiting period. But yeah, so we got a solution. So now we can go into our results and edit it. And this is how we're going to get our streamline. So we'll let it think. Bring this over here. Oh, let me see if there's actually a option to, so like, let's edit this. Let's go into properties. Yeah, there's no 2D option that I see. So we're just going to go back to editing this. So now that we're finally in the results page, we are going to go ahead and do a streamline. So click that, streamline 1. That's sounds good to me. All right. So streamline 1, we're going to domain as the wind tunnel interior. We're going to start from velocity inlet. Equally spaced. We're going to do way more than 25. Let's do like 200. Let's see how that looks. Let's apply that. Cool. So again, it's very similar to our velocity contour. It gives us the same information, except this gives us more detail on the specific streamline and how it moves, the specific particles. So yeah, there we are. And again, we could up the streamline density to get more particles, and it's going to show more coming in at the stagnation point and bending around and compressing around this surface. But there we go. So that concludes everything. That gives us our velocity streamline, that gives us our velocity contour, our static pressure contour, and we're just going to take all this information and we're going to put it into our report, and that should be all. Thank you again for taking the time to watch this, and have a great rest of your day. Goodbye.